Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering. I've been organizing these systems conversations with our prestigious speakers that we bring to Cornell for our Ezra Systems Seminar Series. So today I'm very delighted to have Dr. Sean Barnes, who is an assistant professor of operations management in the Robert Smith School of Business at the University of Maryland. So his research interests include infectious disease modeling, healthcare analytics, agent-based modeling, and simulation, machine learning, and also data visualization. And his current collaborations include with the University of Maryland School of Medicine and also Johns Hopkins University. Of course, we know that Johnson has a very good kind of health research program. So welcome, Sean.
Thank you, Oliver.
I was reading your research portfolio and also your bio. Apparently, I think you have a very good combination of the training and also very good coverage of research interest. So at this point, I think I'd love to know more about yourself, your research, and also your career. How did you, from your undergraduate education and all the way come to this point where I can see that your research is very much holistic, taking systems approach?
Yeah. So I have a bit of a circuitous route to get to where I am today. I studied aerospace engineering at Georgia Tech. So I went to Georgia Tech. I was always very interested in space, and if you're good at math, they tell you to go be an engineer.
Yes.
And so I studied aerospace engineering at Georgia Tech, and I went on to pursue my master's in aerospace engineering as well. During my master's, I realized that there wasn't a specialty area that I was really interested in pursuing further. But I did discover through a research project with a faculty advisor where I was doing simulation modeling of space vehicle trajectories in space using electric propulsion. And I realized that I really liked doing the simulation modeling. And so I started to make the effort to take statistics courses and simulation courses. And I eventually decided I wanted to pursue that further. And so that's what brought me to Maryland, where I joined the Applied Math and Scientific Computation program, which is a very interdisciplinary program structured around applied math and computer science. And then you find an application area. So I connected with my advisor, Bruce Golden, in the business school at Maryland, who was just starting to get into work in the healthcare space. So that's how we started to connect with a group of epidemiologists at the Maryland Medical Center. And that's how I got into this space initially with simulating the transmission of resistant organisms in hospitals. So very much focused on patient safety related applications. And then from there, once I joined as a faculty member in my department now, I've also added this dimension of healthcare analytics. So using predictive modeling to try to drive better outcomes, and mostly in the hospital space. So the talk that I'll be giving later today, we'll talk about two projects that I've worked on with Johns Hopkins at different points of care within the hospital, in the emergency department, and then also for hospital inpatients.
So I think something very important happened when you were doing your PhD in applied math and computing, right? Advanced computing, right? So, I think if you think of applied math and advanced computing, think of that as a hammer. That hammer can be used to hammer any nails.
Yes.
Right. So I think it's more like fundamental, right?
Yep.
Disciplinary, and then you said that you work with your advisor and then find an application area which is healthcare or health systems.
That's right.
Right. So I think this is actually a perfect demonstration of systems engineering. So here at Cornell we have a traditional operating research and industrial engineering department, which is very good in fundamental research. Right. In the meantime, Cornell has a very strong engineering college with a lot of domain applications. So this is exactly one of the motivation, like this system engineering program is created such that the student can be trained with a very solid applied math, computing, or OR, but the student have a very strong interest to have a real world impact by working on a project. So you mentioned this this kind of intersection of your applied math and this healthcare system, you started working with Johns Hopkins. So through this process, did you find that the simulation techniques that you were trained when you were doing aerospace, did you find it useful nowadays when you are dealing with the healthcare system?
Yeah, definitely. The thing I like a lot about simulation is a few things. One, I think it's really useful for the practitioners to go through the exercise of defining the conceptual model for the simulation, because it makes them, explicitly define how they think a particular process works. And so I think there's a lot of value in being explicit about that understanding. My wife works a lot in process improvement, and I think she would tell you that the way you think a process works is not always the way the process actually works. So I think going through that exercise can be really useful. The other thing I would say is, in building a simulation model, you really do have to understand how the various components of the system fit together and work together and interact. And so I think that fits very much with the scope of where you sit, in understanding that, if you focus on too specific of an area, you may not understand how making changes in that area affects other parts of the system. So I think in a lot of the simulation modeling that I've done, you have to factor a lot of different dynamics together to get a more accurate representation of how that system works.
Now I see actually your training in aerospace simulation, where you have to put everything very accurate. Yeah. So now accurate, that's like an engineer approach. Yeah. Now together with the simulation applied to healthcare, probably that's probably the place where like a very rigorous, accurate modeling might not have been applied as in aerospace.
Yeah, that's right. Yeah, I mean, in aerospace, you have all these different disciplines, propulsion and structures and controls, and eventually, right, someone like a system engineer has to try to put all of those things together and make sure that they integrate and interact in the right way. I think healthcare is a field that traditionally relies a lot on silos. I mean, people are very locally focused, and I think a systems engineering approach is what's really needed to make some improvements on some of the outcomes.
Yeah, so I think earlier you mentioned like one of your key research area is actually like healthcare or health analytics, right? So so what can you kind of dive a little bit further into this topic of health analytics? I know this word kind of it's a very powerful word, but underneath this word, what do you mean by this health analytics, and what are kind of the strengths, and also what are the opportunity areas for this health analytics to play a very important role in dealing with improving our healthcare system?
So I think where we are today is really, facilitated and accelerated by, the implementation of health information technology. So many hospitals now have, viable electronic medical record systems. And they're using them in a meaningful way to collect data about the patients. And I think now the next step is how can we leverage all of that data to drive better outcomes in the delivery of care. So this is where I think we're starting to see a lot of predictive modeling applications across the healthcare system. Anything related to emergency department usage, to readmissions, to mortality. The full range of outcomes. And I think, where a lot of our work is focused is not just developing those models, which can give you a lot of, insight about, what features are important as they relate to those outcomes. But I think the next step is, how do we integrate these prediction models into the workflow for the clinicians so that you can support better decision-making at the point of care. So I think really that translation step is the critical component that, I think there's a lot more progress that can be made in that regard. So it's not just the data itself, it's not just the modeling itself, it's how can we translate that to make better decisions that give us better outcomes. I think that's really the goal, and that's what I think the healthcare analytics movement is about.
I saw that you've done quite a few projects in this area. Do you have any kind of example handy so that can help people like interpret what you just mentioned. How can we translate real world problem into this kind of healthcare analytics, and then through all these similar models, and then in the end, actually bring it back to the real world.
Yeah.
Yes.
Yeah. I think that's a very involved process. I think the data and analysis is, as engineers and operations researcher, that's the part we get excited about.
Yes.
I think the translation part takes a lot more work. So to give you an example, the discharge prediction study that I'll be talking about today, at first we had to, connect with a specific unit in the Johns Hopkins health system that wanted to participate in this. So not only we have to collect the data, we have to do the modeling, but then I think the key parts are things that as researchers we are not always as directly involved in. So to give you an example, we have a software developer who's very well studied in the electronic medical record system. And so he can take our predictive modeling, integrate it with the electronic medical record system so that the clinicians can receive those predictions at the point of care. So when they're reviewing the patient's record, they can actually see, their predicted likelihood of being discharged that day. And if that predicted likelihood is high, then that clinician can potentially, make decisions on whether they think that patient can go home the same day or whether they think they need to hold them a little bit longer. And so getting all of that implemented, training the clinicians on how to use the tools and how to interpret, the results of those tools are all things that are required. In some cases, I think change management is an important factor in getting these things implemented. So I think there's a lot of things that can go wrong along the way, but you really have to have engagement with the clinicians. They have to be able to understand the methods to an extent so that they can trust, what you're telling them. The outcomes, I think they need to be interpretable. So there's obviously a lot of trends in the deep learning space and neural networks. But the challenge with a lot of those models is the methods are really advanced. It's harder for people to understand how they work. And in addition, they don't offer as much in terms of interpretation. So it's hard for the clinicians to understand, why a certain prediction is being made, so that they can validate it with their own clinical knowledge, right? So when you find that synergy, I think, is when, they start to trust the tool. They're willing to factor that information into their decision making, and then if you can see the positive outcomes after that, I think that's really where you have the success, and that you can build on that going further. So if you start seeing reduced length of stay by incorporating those discharge predictions into your decision making, which is what we've seen so far, I think that's when you really get the long-term clinician buy-in for that one project, right? And then that can open the door for other things to come later.
In this kind of health care analytics, especially I think people with this kind of optimization background, I think in the end, of course, you want to optimize the operation of the system. And taking as an example, you mentioned this kind of emergency room emergency triage program versus the discharge decision making, right? On one hand, of course, we want the emergency room or something that we want to be able to treat as many patients as possible, but in the meantime, you want also to kind of maintain a certain level of service quality. Right. To this, and how so in this kind of in helping the clinics or the hospitals dealing with this problem, how did you find the trade-offs between among different criteria? Yeah,
I think specific to the triage problem, I think the goal is you want to get the right patients to the right level of care at the right time, right? So the key is to figure out, which of those patients are really critical, urgent patients that cannot wait. And you need to make sure that you identify as many of those patients as possible and get them to the higher level cares as quickly as possible, because that has a significant impact on their outcomes, right? So if you have patients that are waiting because they were under triaged, that can have really, significant consequences for their health outcomes. On the other end, you have lower acuity patients who often wait, right? We've all had experiences where either we were waiting or a family member was waiting for hours in an emergency department, you know, for any number of reasons that it maybe wouldn't take that long in terms of, you know, the type of care that you need. So you need to have some type of attention given to those patients so that they're not, you know, crowding your emergency department. So we have, you know, alternative measures of care like fast tracks, where you may have lower level providers that can, you know, administer the level of care that those patients need, so that they're also getting a high level of service quality, even though their overall condition is not as you know, critical as other patients. So I think, you know, the key is you want to try to address all of those levels of urgency in such a way that you know, they all get the level of care that they need as quickly as possible. And something like the electronic triage tool is trained on those types of downstream outcomes. And so in a sense, you know, you're talking about optimization, you know, it's optimized to make sure that we're getting patients who are likely to have those either serious or serious outcomes. We're making sure that those patients get pushed to the front of the queue, if you will. But then we're also able to identify the lower acuity patients and make sure they get sent off to the fast track. They can get the care they need, and they can also, you know, get back to their home and their lives.
It's kind of basically through like your methods or model that you develop, we can provide like a better match, right? A match between what the patient needs and what service we have there.
That's right. So in operations management, we always talk about, you know, matching supply with demand, and it's the same kind of thing in the hospital setting. Yeah.
So yeah, I was thinking, of course, and a lot of times, so people can always say, okay, if I were given more time, I could have definitely done a much better match and to get. However, because, you know, I was out of time and the system was out of time and there was a congestion, and so as a result, we were not able to do as well as we wanted. So in this case, I feel, and I think one key area that you are doing is kind of predictive modeling. Predictive modeling. So I feel like if you can have this predictive modeling kind of supported, but also by machine learning, that way you could even pre-position some of the resources. I want to kind of dig a little bit deeper. How did you use like predictive modeling in helping resolve some of the key challenges in either emergency rooms or in other applications?
Yeah, so both of these applications are based on predictive modeling, right?
Right.
So in the triage case, we're trying to predict these downstream outcomes, such as mortality or emergency surgery or hospital admissions, and we're using the likelihood of those outcomes to help stratify those patients according to, you know, a more urgent or less urgent triage level. On the other side, by predicting when we think the patients are going to go, and these models are trained on historical data, right? So they're trained on how clinical practice is actually being carried out in that specific location or that hospital setting. So what we're really telling them is, you know, this particular patient, based on your clinical practice, would typically go home today, right? Or they typically would go home in 3 days. And so by putting that information in front of them, it just helps their decision making, right? Or it maybe brings some patients to their attention that they may not have naturally thought about. And that can help drive earlier discharge for those patients. So I think a lot of what we're doing is prediction driven. And in the end, you know, a lot of clinical providers are overloaded, right? They're multitasking and they have a lot of different patients to care for. So I think the way that we view our role is very much in the role of decision support, right? So there's always a lot of tension between you know, the modelers trying to replace the practitioners, and I think we view it as being much more cooperative. And I think that's where we see the best outcomes.
Of course, kind of a lot of times, usually demand is demand is always beyond the supply, right? The hospital, they might be running kind of out of capacity, right? Doing these things. So of course, we've been talking about things focused on in the hospital level, right? I noticed that you've also done wonderful work looking at infectious disease control. So kind of let's now jump out of the hospital, but kind of look at things at either at a national or even global level, since you've been working, I think you've been developing these kind of assisting decision support tools to help the operation of the hospitals. Now, if you look at either hospital operations or healthcare systems here in the US and also across the world, what do you see as the key challenges and opportunities and possibly solutions?
Yeah, I think there are a lot of challenges. I mean, particularly in the U.S., we have an aging population, we have an increase in prevalence of chronic diseases, we have, we have a lot of challenges related to the efficient delivery of care. I think in some sense, the clinical part of medicine, has always been at the forefront, I think. Mm-hmm. And I think the design of efficient delivery systems, was not initially there, and I think we're trying to catch up. So I think that creates a lot of, that relates to a lot of the challenges that we're seeing. But I think, the trend that we're seeing now, where we have, engineers and we have operations researchers coming in with this kind of modeling expertise, and I think if we can find those collaborative relationships with the clinicians, where I think they understand the value of what we do, but at the same time, I think we have to understand the value of what they do, right? I mean, they're very good at what they do, and they have a lot of knowledge about how things work and what the challenges are. So I think, moving forward, I think the opportunities are developing a lot more of those collaborative relationships, finding applications where, that are most suitable for our modeling efforts. And I think if you can find success there, and you can find translation and improved outcomes, then I think that will create more opportunities to, work on things where they maybe would be, initially a little more cautious about, right? Which, so you're seeing a lot with like image processing, and we're finding that a lot of machine learning, predictive modeling applications are actually very good at identifying things in the image processing space. And I think that's a good example of, where historically maybe clinicians would be a little less comfortable about making decisions based on, models and things of that nature. But I think there's been a lot of success in that. Mm-hmm. So I think there's a lot of opportunities to collaborate, a lot of opportunities to leverage these new data sources. But I think translation is going to be the key. Can we actually work to get these implemented and drive better outcomes?
Mm-hmm. Yeah. So speaking of this, you talk about this kind of this big data and also data analytics, and of course now another hot area is kind of artificial intelligence, right? So when people now talk about smart cities or smart future, one of the key area of application is smart health, right? Which is probably, I think, health analytics plays a very significant role there. So with that, so I'm just thinking, you've been developing this decision support system. Of course, this decision support system will keep improving, yep, right? Especially with the data coming in. That's right. You have the machine learning, so this system, they can learn by itself. Yeah. And then if I can raise a kind of very stunning question, people are now, while people are welcoming this AI revolution, but some professionals are worried, like, okay, is AI going to replace my profession? For example, let's say doctors and professors, and then AIs. So first question, do you think that what would be the impact, or what could be the future of AI application in this healthcare system, and what would be the relationship between, you said earlier, at this stage you are developing this decision support. Right. They are not going to replace. Correct. However, in the future, because doctors, they go through a rigorous education and a learning process. Right. However, now with all the huge data, AI, they can learn even much faster, but going through all the historical cases. Right. So what's your view about relationship of doctors and AI, especially health analytics, in the future?
Yeah, I mean, I still view it even long term as being cooperative. I think the key is to try to, maximize the delivery of what the clinicians do best, right? Which is the clinical knowledge and the investigative skills and tying all of that together, but also leverage what the computers do best, right? Which is sorting and filtering through massive amounts of data, right? Which is not something that, as humans, we are ultimately limited, right? No matter how smart or well-trained we are, we can't compete in that front. So I think developing ways that the computer can put information in front of the clinician in the most useful form to help them make those decisions, I think that's the best way. So just to give you an example, I mentioned earlier, the interpretive element of the predictions. Like if the clinicians can understand, why the computer is making this particular prediction, then they can sort of validate, that I understand that makes sense. I agree with that. Or, well, in this particular case, I don't think that applies because of X, Y, and Z. So I think, the challenge with prediction models is that, they're based on large corpuses of data, whereas when you're talking about the delivery of care, that's very personalized, right? It's very individual. So you cannot necessarily take an average solution approach to an individual patient who may be an outlier in one form or another. So I think that's where the clinicians still need to serve as gatekeepers, because they may be able to recognize that for many patients this solution may work, but for this particular patient it's not as appropriate. So I think the big advantage is being able to sort through these massive amounts of data, but then be able to present that information in such a way that really helps the clinician make that final decision.
You mentioned when you were in the PhD program of applied math and computing, right? So now we have a system. We started a PhD program 3 years ago. So actually, when we applied for the approval of this program, actually we intentionally dropped the word engineering with a PhD in systems. So that way, actually, we don't limit the student just within engineering, because even if you look at the hospital system, it's really a human-centered system, complex system, where like a social science. I think you mentioned interpretation, you mentioned translation quite a few times. So now we have this PhD in systems. We just welcomed the second cohort of this PhD student in systems. And in addition, we also have this Master of Engineering professional degree program, where we train students into 1 year this kind of system engineering degree program. So you can see that there's some similarity between your PhD program, applied math and computing, kind of teaching you with tools, but you were lucky to find a very interesting and important application area. So now, for our PhD student or in systems, or even like for systems engineering education in general, would you have any insight or advice from whatever, even either your own experience or what you have observed of all those successful examples?
I think one thing I would recommend for those students is to try to immerse themselves in whatever system they're studying. So what I mean by that is, again, in healthcare we have a lot of different stakeholders involved with the delivery of care, right? You have clinicians, and you have administrators, and you have IT people, and they're all there to support that common mission, but they all have different, I think, challenges and things that they're facing. So I think one thing that I've learned over the years a lot is, from the clinicians, I kind of, understand what they're facing, right? And I think, and understand, what, their assessment of the problems are. And I think by being able to incorporate that into your modeling, it makes the modeling so much better. And, in understanding, what their potential solutions are, I think is really important. So again, from a systems approach, I think it's really important to understand all of the pieces and how they fit together and how they work together. And that involves, talking to all of these different stakeholders to understand how they think the process works and you know, what their individual problems are, because it can vary from stakeholder to stakeholder.
Yeah, I agree with you. I think that's actually, I think it's the root and where things should start, right? For any kind of research, especially for system engineering research.
Yeah, but again, from the process improvement folks, they would, you know, see the process, right? So wherever it is, you know, go see it, talk to people, try to understand how it really works. I think sometimes as the modelers, you know, we like doing the coding and we like using the software, but I think, you know, only good things can happen by you know, involving yourself in the process more.
Do you have any question regarding our program or anything that you would like to ask?
Yeah, I mean, I'm curious about, you know, where people go when they're finished.
Good question, but you know, our first cohort now they just they just finished their qualify exam, so they are starting their thesis work. But when we designed the program, so basically, so kind of we were aiming for these PhD graduates to serve, of course, like the academia, right? So they can go to that area. And the government agencies, for example, of course, NASA, like aerospace, and a third area is basically industry. Like, so that these are the areas, of course, at higher level within that those organizations. But we did kind of envision 3 types of PhD thesis. Like one type, more like kind of the traditional applied math, or what we call methodological. Kind of you can, because we do allow students to go into that. And another area is kind of system integration. You know, it could be an existing fundamental theory, but applied to a domain where the theory was never applied before. That provides the student with an opportunity to innovate. So we call system integration. And the third one, actually, we are also open to prescriptive, kind of totally qualitative. You don't have, because a lot of time, like as academics, we are, if you don't have an equation, we feel, right? However, we feel like, you know, a lot of social science science discoveries, they don't have to be like kind of mathematical, right? So, because the Cornell, you know that system engineering has a deep root in military applications and aerospace. Right. So, however,
I noticed the military science building walking in, which you don't see everywhere.
That's true. But we hear one of the key things that this program will emphasize that we are also, in addition to covering those traditional systems application areas, we also emphasize what we call commercial systems. Okay. Like commercial systems, like, you know, like urban systems, or kind of cars. Right, that manufacturer systems, and now we are even emphasizing more on like human-centered, complex systems. We feel that today's world, a lot of system challenges have so much to do with the human factors. So that's why in our curriculum we also have, like, you know, the choice modeling, behavior modeling, even, you know, some psychological courses. So that way the student can work together with the social scientist.
You know, I do agent-based modeling, and a lot of that has roots in the social science discipline. So when I first started applying these models in the hospital setting, that was fairly new at the time. But I think, you know, the great thing about it was starting to get people to think about individual behavior and interactions between different types of individuals. And so I think it's a really important aspect, right? I mean, even with all these systems, we tend to treat them as if they're automated, mechanical, etc. But you know, there's people driving a lot of these decisions, and I think understanding the decision process that they consider is really important to understanding how the system performs.
Wonderful. Thank you, Sean. Thank you again for visiting us.
Thank you.
Yes.